All right, this next video is pretty simple at its heart, but it's got lots of truth table practice and kind of some linguistic fun. Oh, and a little surprise with mathematics. So I am excited for it, and hope you are excited for it as well. So we're going to start by looking at this truth table. This truth table is, again, just kind of some silly truth table that is taken from the book that is used to talk about when is this proposition true and when is this false. So super messy, super ugly, and really doesn't have much meaning for us. But what you'll notice, and I highly recommend that you do this as practice if you want to actually create this truth table on your own. Don't just take my word for it. Don't just take the book's word for it. But again, notice here that the author is kind of using shorthand for things as well. So they're saying, okay, let's let the spade mean this nonsense so we don't have to write it all out. Again, let the heart be this nonsense so we don't have to write that all out. And what you'll notice for this specific compound proposition is that it is always true. This is what's known as a tautology. It is something that is always true. So again, this thing right here, which he is denoting with a white heart, is always true. Again, that's pointing to this proposition. That's what's known as a tautology. So a tautology is just a proposition that is always true. So here we have a compound proposition that is always true. No matter what x, y, and z are. We go through enough logical hoops that the result is always true. Now, you may have heard the word tautology used in English. That can refer to rhetorical tautologies as well as logical tautologies. So some examples of rhetorical tautologies is like, do you want a free gift? It's like that redundancy. It's like, well, if it's a gift, isn't it already free? Or like police apprehended an armed gunman. It's like, well, okay, that's, again, kind of rhetorical in a sense. It's called, or I meant redundant, but that's called a rhetorical tautology. There's also logical tautologies in English, like saying like, well, it either it is or it isn't, or something like that. It's like, well, yeah, duh. Like by definition, that's true. Or if you say like, the book is popular because people like it, or because a lot of people like it, right? It's like, yeah, that's self-explanatory. It's obvious. It's self-referential. But here, what we're going to talk about for tautologies is just a statement that is always true. Okay? So basically, we're just going to get some practice with two truth tables. I'm going to have you look at a couple, and you're going to tell me which of these are tautologies. And then we'll talk about some fun stuff that result from all these. So one of the reasons why tautologies are nice is that they can be used to show that certain things are identities. They're able to show that certain things are the case, because if we have something of this form, that's a tautology. Essentially, that means A and B are the same thing in some sense of the word. Okay, so here's your practice. Letter A is going to be X or not X. And again, just saying it out loud, I'm sure you know the answer, but you can show it with a truth table. The second one is not X or Y, equiv, not X, and not Y. Now, we've seen something similar to this when we talked about sets. Remember that the not is just kind of like set complement, or is like union, and is like intersection. So hopefully you already know what that one's going to look like. Here's another one. X and Y or Z, equiv, X and Y, or X and Z. So I really do want you to get some practice creating these truth tables. And again, use this as a model for the truth tables. Start on the inside and then just add more and more things and just be very clear. Like, okay, it's like, oh, if I want A and not B, I'm really just focusing on these two columns. And then start on the inside, work your way until you have what you need. To find out when are these true, and to remember if they are always true, then you've got a tautology. So pause the video, do those out. I am not going to do these out during the video. So if you do the first one, you're going to see that X or not X is, of course, a tautology, right? It's always true. Either X or not X will always be true. And in fact, we could have changed this to be XOR as well, and it would still be a tautology, because X and not X are mutually exclusive. They are never going to be true at the same time. So in that case, X or and or are essentially the same. This is called the law of excluded middle. It's kind of saying either something is true or it's not true. There's no middle ground here. For very binary things, that of course is true, but for other things, it's not going to be true. It's just like, are you having a good day or a bad day? Well, most days are somewhere in between. But for this kind of binary propositional logic, that's what this looks like. The next one, I again am writing this one with a little shorthand. I did these one by one. And I called the first thing heart, second thing circle, and I showed that circle and heart are equivalent. Basically just going through this. This is De Morgan's law, right? The complement of X union Y is the same as the complement of X intersect the complement of Y. All right. De Morgan's law can also be used in probability. You may have seen it there before as well. But yeah, the idea is these are indeed equivalent. One of these, right? And remember, equivalent means they're either both true or they're both false. And you can see that is certainly the case here. Finally, they're all tautologies. This is the distributive law, right? We were looking at, in letter C here, right? It's essentially we're distributing this and. X and Y or X and Z. That's exactly what we're doing here. This is the distributive law. It certainly works. And again, just like before, they're equivalent because they're either both true or both false. And we get into something really interesting when we talk about this distributive law. It's that in some sense of the word, again, here is the distributive law for logical operators. In some sense of the word, and is like multiplication. And in some sense of the word, or is like, addition. Right? Because that's really what this is. This is like a multiplying, and this is like addition. And we're saying like, yeah, it's like the multiplication plus this multiplication. And here's where it gets even more interesting. And is like multiplication, or is like addition. Let's go back to our truth tables for operators. This is and. This is like multiplication. What do you notice happens when you multiply these two numbers together? Yeah, 0 times 0 is 0. 0 times 1 is 0. It is like multiplication, right? And similarly, is this not like addition? All right, well, it's not perfectly like addition. 1 plus 1 is not equal to 1. But it's like addition, right? It's like, you're adding things together. If they're both 0, you still have 0. If they're not both 0, then yeah, you got a bigger number. All right, so in some sense of the word, it is like addition. So that's kind of a fun little fact that I appreciate. But yeah, this video is basically on tautologies. Tautology is just kind of some proposition that is always true. A lot of times we talk about compound propositions that are always true, and we'll figure out whether something's a tautology with the truth table. Let me know if you have any questions, and until next time.